George Ogilvy, and this is Physics 2211, Lab 4. In this lab, we connected the experiment with a spring and a mass. We extracted the data using the tracker app and by tracking the motion of the mass as it moves diagonally on a spring, and then we use closed-up to simulate the model and compare the two results. The main principles and formula we used involves energy, including kinetic energy, which is K equals 1/2 mv squared. Potential is 1/2 ks squared. Gravitational potential energy, which is mgh. Position update formula, as well as the velocity update formula for the model using closed-script. When we use the tracker, we pretty much pulled the mass from the spring to a diagonal point on the spring and let it go and recorded a video as the mass moves in oscillation. We conducted this with a mass of 200 grams, which is 0.2 kilograms, and tracked the data. And here you can see a little screenshot of the tracker app showing the screenshot of the video and the graphs. Before we were able to use data for anything closed-script, we first had to find the spring constant as well as the relaxed length of the spring, because we couldn't measure the relaxed length of the spring during the filming of the video. So we used two sample weights. We had a mass hanging at equilibrium with two different masses, and then we used the formula mg is equal to force, which is equal to KL1 minus L naught, with mass 1/2 a kilogram, which is what we found. And we also did that with the second mass, which was 0.1 kilogram. We set them equal to each other we set them equal to the spring constant and set those equal to each other to find the relaxed length of the spring, and then use the relaxed length of the spring to find the spring constant. Aside from that, we used a different mass of 0.2 kilograms for the experiment of the mass moving in oscillation with the spring. So here you can see all the code we have. We have the regular energy formula and the position update formula and the velocity update formula and the net forces. And then we input the weight's mass of 0.2, and then the initial position vector that we extracted from the tracker video. After putting all the data from the tracker app into the computational model, we then ran it, and here you can see the graphs. That was the output. You see the change in energy versus time, you see the position versus time, and then you see the y position versus time. And the computed model is in the blue for the two right graphs, and then the experiment that we measure with the tracker app is in red. Here you can see there's a pretty big difference, especially in the y position versus time. It's just probably due to the angle of the camera not being perfect 90 degrees pointing towards the system. And that would cause a skew y position, of course, as the meter stick in the tracker app is directly vertical, and the camera could have been slanted if it wasn't at a perfect 90 degrees. Lastly, for the what does it mean question, the question is if the energy principle is satisfied, and you can see it is, because throughout this entire experiment, energy is conserved, and the change in energy is always going to be equal to 0, which means the energy is never destroyed; it's only transferred. It's only changed from certain types of energies to another. And for the what if, we found the oscillation period, and the extraction was approximately 1.13 seconds. And the period of oscillation in the y direction was approximately 0.91 seconds. There's a pretty big difference, and this is due to the extra force of gravity acting in the y direction.